Most consensus methods belong to one of two families: longest chain wins models, which are used in chains like Bitcoin and Cardano, or BFT-based models, which are used in chains like Cosmos. Longest chain-based consensus methods are typically more robust and allow for a high level of decentralization, whereas BFT-based models typically allow for much faster and more concrete finality at the cost of having a limited number of validators who can participate in consensus. Avalanche uses a style of consensus method that doesn't really fit into either family. In theory, this new style of snow-based consensus methods allow for a large number of validators, like the longest chain methods, whilst also having fast finality like the BFT methods. In this video, I'll go over how these methods work. For Avalanche, there are multiple chains in the main ecosystem which use different underlying data structures. The consensus method for each is different, so I'll explain the DAG-based consensus method first, and then go over the blockchain version later in the video. The DAG structure that Avalanche uses is leaderless, so any validator in the network can add a transaction to the chain. Each transaction in the DAG has to reference two or more older parent transactions, so the chain never goes backwards. It's also using the UTXO model, so it's easy to spot conflicting transactions, as they will be trying to spend the same outputs. So when a new transaction is added to the DAG, a validator just needs to check if it's valid, and to see if there are any other conflicting transactions. It will then make a decision on if it likes a transaction or not. But then, it also needs to find out if there is consensus between the other validators over also liking the transaction. To find this out, it will use random subsampling. Random subsampling is the same method used in polling to get an approximate opinion of a large population from a small random subsample of the population. The opinion of this subsample is unlikely to be the exact same as the entire population, but should be a good approximation. So if I'm a validator and I receive a transaction, first, I will check its validity and for conflicting transactions. If there are none, then my initial opinion will be to like the transaction. Then, to see if there's consensus with the other validators over liking the transaction, I will choose a small random subsample of the other validators in the network and ask them for their opinion. Based on the opinion of these other validators, I will then update my opinion of the transaction. If the majority of the subsample, including my own opinion, dislike the transaction, then I will switch to also disliking it. If any other validators poll me, this is now the opinion I will tell them. This first round of subsampling will give a rough opinion of the other nodes, but is not enough to be confident that the majority of validators in the network have the same opinion, so I will need to do multiple rounds of subsampling of the transaction to increase my confidence. I will continue to do rounds of subsampling, and if the opinion of the round is the same as the previous one, I will increase the confidence score of my opinion of the transaction. If the opinion changes, I will reset the confidence counter back to 0 and start over. Other validators will also be doing the same subsampling process and updating their own opinion of the transaction, so even if at first, in the worst case scenario, the opinion on approving a transaction is 50-50, the random subsampling will randomly tilt the opinion in one direction, and after that, it should snowball into having all the validators sharing the same opinion. After the confidence counter of a transaction reaches a set value where it's statistically likely that the majority of validators all share the same opinion, it can be considered final. This is probabilistic finality, however, the confidence threshold is set up so that the chances of it being wrong are extremely small, to the point where you're more likely to find a collision in a hash function. This is the rough idea behind how snow-based consensus methods work. All validators will constantly poll other validators, and try to change their own opinion to be in the majority until they are statistically confident that all other honest validators share the same opinion. This is the simplest form of the consensus method, and does work, but having to do this for every transaction isn't efficient. To improve efficiency, Avalanche is able to take advantage of its DAG structure. Due to how transactions have to reference multiple parent transactions, if you're voting that you like a child transaction, you're also implicitly voting that you like the parent transactions as well, as the child wouldn't exist without the parents. This implicit vote also goes for the parents' parents, and their parents as well, all the way back to the first transaction. This means instead of having to do multiple rounds of subsampling for each transaction, you only need to subsample the latest transactions, and the results for these subsampling rounds will also increase the confidence score of the reference transactions as well, meaning you can do significantly fewer subsampling rounds to confirm a transaction. In the case that all transactions referenced were honest, this works great, but if there are double spends within the reference transactions, validators may vote to reject an honest transaction because their parents are conflicting. For these cases, validators will bundle any orphaned, non-conflicting transactions together and reattach them to a known honest part of the DAG, so they can be voted on again without the conflicting parents. For the majority of transactions, consensus is super quick, as validators will be doing many subsampling rounds per second, so it won't take long for their confidence count to reach the threshold number and become final. It's only really people who are submitting conflicting transactions at the same time who have to wait longer for finality. So far, I've described a consensus as treating every validator equally. However, for cryptocurrencies, this could easily be gamed by someone creating millions of validators on virtual machines, so a form of Sybil protection is needed. For this, Avalanche uses proof of stake. For the random subsampling rounds, instead of each validator having an equal chance to be selected, the chance of selection is weighted by the amount of tokens the validator is staking. This means an attacker can't just set up millions of nodes with zero stake, as they would never be subsampled, so it wouldn't affect consensus. Within the main Avalanche subnet, there are 3 chains running: the P chain, the X chain, and the C chain. It is within the P chain that stake is handled. Validators will send a special transaction on the P chain where they lock up their stake for a certain period of time, and when validators need to do a subsampling round, they can look at these transactions on the P chain to find each validator's weight. The DAG structure is how the X chain is built, but the most popular chain in the Avalanche ecosystem is the C chain, which uses a blockchain. The big difference with blockchains is that now there is only one tip on the graph where new blocks can be added, instead of the potentially infinite on the DAG. This means the decision that needs to be voted on is now more complicated. It's no longer a simple binary yes-no vote on if a transaction should be added, but a more complicated decision on which of the potentially many blocks should be added, who are all competing to be added to the same tip of the graph. For example, if there are 5 validators in the network, 5 blocks have been submitted, and each validator prefers a different block, then no matter how many subsampling rounds there are, no one will ever get a majority in the subsample for any block, as none of the blocks have close to 50% of the votes, so none of the validators will ever change their opinion, and the network will stall. The way Avalanche solved this problem was by splitting it back up into a series of binary decisions, so the same subsampling model can be used again. Each block submitted will have a unique block hash, which is a 256-bit binary number. Avalanche uses every bit in this hash as a binary decision to vote on. So now, when subsampling, nodes will ask other nodes what they think the first bit of the block hash is, then the second bit, then the third bit, and so on. Well, actually, they pipeline the process, so they don't have to vote on every single bit, and it's only really the conflicting bits that increase the number of subsampling rounds. Here's an example where there are 3 blocks submitted, and let's say the network is evenly split, with each block having 1/3 of the validators liking it. Instead of individually voting on each of the first 3 bits, validators will vote on whether they like 1111 or 1110. In this case, 2/3 of the validators like 1110, so it will likely win. This then rules out the first block. Now the next 2 bits are also the same, so they will vote on if the 4th, 5th and 6th bit are 1110 or 1111. In this case, it looks like a 50-50, but after a few rounds of subsampling, randomness should push consensus towards one of the options. Let's say 1111 wins. Now, the second block will be ruled out, so there will be consensus that block 3 is the winning block. Even though there were 8 bits, due to pipelining, you only needed to do 2 subsampling rounds to reach consensus, instead of needing to do a subsampling round for each of the 8 bits. This change allowed for the subsampling model to work on a blockchain, and at first, this was how the C chain ran. However, because they kept the protocol leaderless for the blockchain version, and there is only one tip where people can add blocks, it ended up with many validators posting blocks to that one tip, meaning there were many conflicts that had to be voted on, causing a lot of rounds to be required to make a decision on which block to choose. This made block times inconsistent and slower than desired. To make it faster, they ended up switching away from the leaderless model to now electing a leader who gets to create a block, so there are less conflicts and the subsampling model can reach consensus faster. This leader election works by first getting the list of all the validators from the P chain and ordering them by node ID. Then a seed number is generated by taking the chain ID and XORing it with the block height. This should produce a seemingly random number for every block. This seed number is then used in a sampling function to sample the validator list by the amount they have staked, to then select a list of 6 validators. The first validator in the list then gets 5 seconds where they can produce a block. If they don't produce one, then the second person gets 5 seconds, then the third, then the fourth, then the fifth and sixth. When they produce a block, the 256-bit block hash is subsampled among the validators, but now, because there should be no competition, the entire 256-bit hash will be voted on at once, and consensus should be reached very quickly, as there will be no conflicts. If none of them did produce a block in that time period, then it goes back to the old leaderless method, where it becomes open to everyone and any validator can produce a block. A potential problem here is that the randomness is predictable. The chain ID is a static number, so you can pre-compute the randomness for all the block heights and create a validator with a node ID that will win a block. However, whilst this is possible, you need to lock up 2000 AVAX for a minimum of 14 days to register a validator on the B chain, so can only do the attack once every 14 days for every 2000 AVAX you have. So whilst you may be able to cause a short delay every so often, it's not something that will cause a problem unless an attacker has a significant number of AVAX tokens. The big advantage of snow-based consensus methods is that they can be extremely fast. If there are no conflicts, you can easily run many subsampling rounds quickly and come to consensus in under a second, which is incredibly fast for a cryptocurrency, especially as this can be done even with a large number of validators. However, they do have some downsides. Firstly, they do sacrifice some robustness to achieve this speed and decentralization. Longest chain wins models can typically survive with 51% honest validators, BFT models with 67%, but it looks like snow-based consensus methods need 80% honest validators to guarantee liveness. Secondly, slashing is a method where some proof-of-stake-based protocols will punish validators who clearly break the rules by slashing the funds they have locked up. This brings extra security as it provides a disincentive to misbehaving. It is somewhat divisive, so for many people, the fact that Avalanche does not have slashing will be an advantage. However, even if it wanted to, it does not look possible to implement slashing with snow-based consensus methods, as it is normal behavior for validators to switch their opinions, so it's difficult to differentiate honest from dishonest validators. Many other consensus methods don't have slashing either, but could implement it if it turned out the extra security was needed. With Avalanche, they can't. Thirdly, whilst the consensus method is cheap and efficient between validators, it is more expensive for normal nodes to validate. Normally, a node just needs to check a block hash or some signatures to confirm which block there is consensus on. But with Avalanche, they need to do the subsampling rounds on the validators themselves. In order to do the subsampling rounds, Avalanche validators need a direct connection with all other validators in the network. If a normal node also wants to be able to validate consensus, then it also needs a direct connection with all the other validators in the network. This could be a limitation or potential attack vector, as there is no Sybil protection on setting up a normal node, so there may be the potential to set up millions of them to overload validators with connections and subsampling requests. This wouldn't take down the network, as validators would simply prioritize other validators over normal nodes, but could lead to honest nodes being crowded out and not being able to read consensus, and limits the number of people who are able to run normal nodes themselves. Still, none of these disadvantages are particularly big, so the advantage of incredible speed will make snow-based consensus methods an extremely attractive option for any applications where speed is important. If you found the video useful, please leave a like, and subscribe if you want to catch my future content.